Hello. Good afternoon, everyone. Thank you for coming. My name is Ivan Baev from Sci5, and I'll moderate this panel on high-level intermediate representation for a C++ optimizing compiler. Note C, C++, and optimizing qualifiers in the title. We want to focus on mainstream programming languages from performance optimization point of view. What was the motivation for organizing this panel? As you may know, most current and past C and C++ compilers use a high-level intermediate representation. LLVM has been an exception, partly because of very expressive and extensible LLVM IR. However, with wide adoption of MLIR, I think now is a very good time to address this gap and create exciting opportunities with high-level intermediate representation in LLVM compiler. Adding such important change to compiler infrastructure can and will impact many organizations, their products and roadmaps. It is a challenging task to make it right for all users and developers of LLVM. So the purpose of this panel is to present a spectrum of possibilities and discuss their trade-offs toward building a consensus on the next step. It's my pleasure to introduce our distinguished panelists today. Johannes Doerfert from Lawrence Livermore National Lab. He came 3 weeks in Bay Area. Welcome. Bruno Lopes from Meta. Mehdi Amini from Google. Chris Lattner from Modular, co-founder of LLVM. And Alex Zinenko from Google Research. Each of our panelists has made significant state-of-the-art contributions to LLVM in areas very relevant to this panel. We will begin our discussion with questions on kind of optimizations that will benefit from high-level IR, agreement or not on MLIR as the primary candidate, desired features of such intermediate representation, connection to the front end, support for cross-module compilation, and of course, new promising developments in this area. We'll begin with hearing opinions of our panelists on these topics, and then we'll follow up with questions from you, the audience. So let's start with type of high-level optimizations that we hope will benefit from high-level IR, or at least their maintenance will be easier with such high-level representation. So I'd like to ask Johannes to begin this discussion.
Thank you. Yeah, as people may or may not know, I'm probably the antagonist on this panel. So I'm not actually working in MLIR. So that just as a precursor to all of this. And I think at the same time, so we need high-level optimization for C, C++, and what I work on is like OpenMP, which kind of sits on top of them. And then, you also have all of the C and all of the C++ and Fortran, all of that there. So we want high-level optimization. I want high-level optimization for these languages. And we have a lot of that code in that languages. So we really care. The question here really is, how do we encode our knowledge about those languages? And how do we approach this? And there's various angles, and I'm not going to detail. I'll just try to put all of you into a mode where you look at things from various sides. Like, what about disruptive changes? What about timelines? What about compile time? What about going there incrementally without losing out features that we currently have? Those are things that we have to consider whatever we decide to do. And as kind of, when people think MLIR and they get high-level optimization, they think of linalg and transform, and then they can do tiling. And that's great. But if you come from a language like C, C++, where aliasing is a thing, things throw exceptions that are well-defined, long jump has been invented, there is something that does break, continue, all sorts of miserable things that people came up with over the last few decades. It's not as simple as, oh, you can always tile, or you can just pretend every loop that somewhat looks affine isn't a fine loop, and we go from there. That ain't how any of this is. And you have to kind of keep that in mind when you think about high-level optimization of C, C++. And I spent a lot of time trying to get C, C++ or LLVM IR into the polyhedral model, which is your affine world. It's hard. Anyway.
Also, Johannes, to anti-antagonist, I think that you're assuming people will try to turn C++ into machine learning stuff, right? MLIR is useful for things that are not just doing the ML. And so, in Circuit, there's a lot of work to do hardware design and things that have nothing to do with these domains, right? And so I think if the question is what kinds of high-level optimizations are interesting, I wouldn't even start with linalg or things like that. I would start with the LLVM loop optimizer is not great. Right? And so if you agree with that, then you agree that, and it's not that people haven't tried to make it better. I think that there are fundamental issues with LLVM IR that lead to that domain being challenging to tackle in an effective way. And so if you agree with that, then you say, OK, cool, let's build a loop optimizer, right? That's actually good.
Question is, how many of those issues do we inherit from C, C++ rather than that they stem from IR in the first place? And if you say they do stem from IR, we own it. We can change it.
OK, but so there exist good loop transforming C compilers. So I think there's existence proofs that show that it is not, C is a challenging language and C++ is challenging in various ways, right? But it's not a science problem. It's an engineering problem.
Yes, I know. But they do things like, oh, let's try out this vectorization factor, go till the end, see if the assembly that falls out looks good, and if not, track back to the beginning and do something else. They make design choices that we explicitly try to avoid. So it's, yes, you can do it, versus, yes, you can do it in a reasonable way.
No, again, in terms of having a productive discussion, my read here is that you have a specific, using MLIR in Clang means 17 things, right? Wherein you could start by asking a question of, if we were to do this, what do people think are the best way to do it? And it may be a very different set of discussions and set of trade-offs and set of applications. And I absolutely believe you that many people say, oh yeah, then you use linalg and magically everything's awesome. I would not be one of those people, personally, for a variety of reasons. But we can work backwards from that. So I agree with you. Set jump has been invented.
So maybe I'd like to follow up with what you were saying on the, if the IR is the problem, we can change it, right? And the problem is how flexible it is to change the IR, how easy it is to do something. There used to be loop passes, I think, in LLVM, where LLVM was constructing this construct which didn't exist in the IR, and trying to persist it through some passes. And that was very fragile and very difficult. And I think we're hitting the limit of the flexibility of the LLVM IR. And some of the things that MLIR allows you to do by allowing multiple levels of abstraction or easily extend it is to say, and you mentioned poly, for example, earlier, is to say, I'm going to materialize the results of some analysis of some raising, for example, in some region of code. And those become first-class IR constructs that you can operate on.
And because they're first class, they not just become easier to work with, they can be serialized. You can have tooling that works with it. You have all the other affordances, location tracking, all that.
Let's do that. Nikolai already suggested doing that, and let's pick a few that we can make short-term use of in IR, and have a loop construct or whatever we need. I'm just making something up. But yes, we can evolve it. That's why I'm saying we can modify it.
So you're saying, why can't we make LLVM IR better to solve the problem? Is that the question?
I'm saying we might want to adopt ideas that came from. We might want to adopt ideas that came from MLIR that turned out to be useful and want to evaluate them on LLVM IR in an effort to both get these things closer, and maybe even do at some point merging. And even if that is not the case, we have only one concept now to think about as a community rather than two concepts. Like maybe we get rid of thighs and do a block argument, and then we have less to think about, which would be cool.
Well, so I mean, you can be very reductive about this, and you can say software is just bits, and like all we do is we turn zeros into ones and ones into zeros and rearrange the bits, right? And so therefore, everything's the same, right? But you can also be kind of pragmatic and say, okay, cool, let's first start by what is the right thing? Like, let's gain consensus and build a shared understanding of what we want the world to look like when we're done. And once you have that shared understanding, which I don't think we have, but once you have that shared understanding, then you can say, cool, we're way over there. What are the logical set of transformations and steps to get to where we want to be? I love the talk this morning. I think that one of the challenges I would have as an old school LLVM loving person is the fear of partial transitions. And so we have had many cases where, I won't name specific projects, but it gets like halfway done and it never gets completed, or it takes many, many years for things to get completed. I think that one of the things I'd be concerned about is making sure we do this in a way where each step is bounded and I think shows benefit and things like that. But the execution side of such a change, I think, is very different from the what does success look like phase. And so maybe it can be better to say, like, what is it that we want to achieve? What are the problems in Clang? Like, forget about MLIR maybe, which is kind of your point. What do we want to achieve? And so it's like, hey, a loop transformation system that is extensible. Well, it turns out some people do want to burn huge amounts of compile time to get slightly better code. Not everybody, right? We don't want that to be the default necessarily, but having that in the toolkit would be valuable, right? And even those polyhedral things can be useful, I hear, right? They should not necessarily be the only thing, but it's about how do we design a system, which I think LLVM has done well, that can be used in many different ways and composes correctly.
So we hear loop optimizations, but any other type of optimizations that are likely to benefit?
Well, I was going to ask, like, so far we were talking about like a language level optimization, like loops and like exceptions. But it feels like a lot of optimizations we actually want to do in C++ are more on a library land. Like, we need to understand the semantics of what a vector is. And we need to understand the semantics of like containers, algorithms, so we can optimize and substitute implementation of those. And that so far it was like outside of what we actually want to do in Clang. So everything that needs to understand the library goes into a separate tooling. So like, is it the right time to reconsider the choice, or are we building multiple tools?
Well, so, I mean, just to plus one you, one of the interesting things about C++ as a language is this notion of building zero-cost abstractions. Right?
Yeah, but when they're really zero cost.
Well, so yes, I agree with you. Where I was going is a little bit different, which is C++ does not provide that when it does things like constant folding on the AST. Because if you introduce an abstraction and then it gets inlined away, that optimization that happened on the AST doesn't happen after inlining.
Yeah.
Right? And so there's these things that because of, you could call it phase ordering, you could call it many things, like it breaks a lot of the value of zero-cost abstractions that C++ gives you, and allowing library developers to make it so like plus on std string could be constant folded. Things like this, not rocket science, but again, I'm agreeing with you, right? That would be, I think, pretty profound for the ecosystem.
Yeah, so, and then it might not be, like, are we looking at two different things? Are we looking at one thing that understands the library and then another thing that doesn't care about library? Like, and one is lifting an LLVM and another is based on MLIR? That sounds crazy.
Well, I think that you have to decide what part of this elephant you want to tackle first.
Which means we want to tackle both of them anyway.
What's that?
Which means we want to tackle both of them.
Well, so again, maybe being the curmudgeon, the antagonist, I don't know. I mean, I think that there's a risk of saying, let's do 50 things all called add MLIR to Clang and do them in parallel. I think that there may be, a good skunkworks project. I've advocated in the past for like help improve the stack analysis infrastructure and stuff like that as an example of something that is like known to be suboptimal and is not in the critical code gen path. And I think that could prove a lot of design points.
I mean, the library thing is something. I mean, I would also first, prototype something else to determine what do we have to gain before we do big things. And with our experience was both in the OpenMP runtime and when we did the LibM for GPUs experiment, if we had C++ runtimes that don't have header code, we could embed domain knowledge about the runtime calls easily, and we could try stuff out. And then we can play around with this and figure it out. The problem is we kind of expose everything directly, and then the header code and other things like that. And then we're kind of in this weird land where we don't really know anymore if it's really just this vector push or if it's 3/4 of a vector push because we moved something out. And that's problematic.
Yep. So Bruno, you have been working on this.
Yep.
I don't know very much about what you've built. But I kind of agree with Ivan that there's a huge amount of responsibility here to make such a big change to something like playing. How do you think about this?
Yeah, so to start talking about that, let me give a bit of background for those who don't know what we're talking about. So at Meta, we've been working with developing Clang IR, which is a new IR that sits between Clang AST and LLVM IR, if you look at the Clang compilation pipeline. And our main reason to be working on that is that we have millions of C++ lines of code, and the fewest amount of percentage of performance we can get there can translate in millions, like saving a bunch of resources. So, well, it's a big road to get and substitute those intermediate pieces. But if we think about optimization, I think there are like 3 main axes that I see here. Well, first one is C++ is hard. There are lots of edge cases. There's lots of details. Clang can't help itself. Whenever it sees the first opportunity, it inserts a mem copy somewhere, completely I don't care if this was a move assignment or not, puts a mem copy there. So I see this, there's one realm, people like to think, well, I would like the compiler to maybe rewrite my vector code here, my stud vector code, to put a reserve before, right? That's the naive thing we like to kind of project when we talk about that. Well, but if you do that, you might be breaking some assumed semantics, because when you put a reserve that thing might reallocate, and then you're changing whatever expectation you had for the control flow of that code. So the first axis I'll think about is code modification tools. If I have profile information, if I have the technology for understanding higher levels of C++, one first naive thing we could do is rewrite code, or suggest code rewrites, or produce diffs that the user can decide to apply or not. So this would be the first realm of optimizations I think are interesting. Not optimizations per se, but it will yield good performance.
Tooling, yeah.
Yeah. So a second one will be, well, now that we have a more expressive IR, why instead of necessarily rewriting new optimizations, why we don't try to generate more reliable metadata so that we can code-gen an LLVM and the existing optimizations can kick in better? So just a simple example here is if you're writing C++ and there's, and if you're using lots of temporaries during calls and et cetera, and you get into the weird rules where you have a full expression and you might or might not extend the lifetime. And the way that we currently Clang code-gen that is that it will shove the allocas in the entry, in the beginning of the first base block. And it's unless you were actively trying to track lifetimes, you're already losing that information. The only place where we kind of force the lifetimes to go on an optimization pipeline, as far as I know, is when we're dealing with coroutines, because those requires it. So I think if we can provide more reliable information about using metadata to kind of translate better things that memory SSA could look at, alias analysis can look at, we could probably allow those optimizations to kick in way better. So that's the second axis, I think. And the third one will be to actually go and rewrite, put transformations on top of Clang IR, or generate the necessarily dialects that you want to use for a certain a pipeline use case, let's say, to do all the interesting things. If you look at just as we've been working on doing like C++ code gen, we very often hit those points where Clang is doing like early optimizations, and we can see that how hard it might get in the future, like when you're down to LLVM IR to kind of reconstruct all of that. So that will be, a simple case would be if you just look at those like temporaries and things, you see that they have very like short range lifetimes. A bunch of objects are created, populated, and just used as an intermediate step to actually populate the original memory for a variable, because that's how C++ works. It will force you into like building a temporary before doing the assignment, and et cetera, et cetera. So by being able to better look at those things, I think we can do a better job.
Thank you, Bruno. So one practical question is connection to the C++ front end. So with that, I'd like to ask Alex to share his view on the challenges.
Well, and you've also built this with Polygeist.
Yeah,
right?
so we have a kind of front end. So that's, I guess, the reason why I'm on this panel. So we have a thing that started as a like, toy project. We had MLIR, we had Clang. So how do we connect the two things? So, and there are basically two main ways. There is a proper way to have a Clang code gen that emits a different IR. So that IR can be, MLIR can be like a different representation, whatever we want. Or we can do a simple thing people learn in grad school and go read the Clang AST and try to like, emit bypassing code gen. We took the second approach because it was significantly faster, and it also was modular in a sense. So we could support like a subset of C++ we cared about, or a subset of CUDA we cared about, because we also support that. And that's one of the challenges I see if we want to replace the connection of the Clang frontend, assuming like we all want a Clang frontend here in LLVM meeting, connecting that without needing to connect the entire C++. And then if you look at what C++ AST is, like the joke in Clang is, it's neither abstract nor syntax nor tree. So, and then because everything, like in a couple of steps, you go back to some sort of like root of your AST, you're kind of stuck trying to convert, like I only want to convert loops because we all care about loop optimizations. And I'm fine having lower level IR inside loops around. I just want my for loop because that's what I want to optimize. And it's a challenging thing how to get that. And then there's a stretch goal, and the stretch goal is why did we even start to build this? And I see a lot of people writing C++ are actually writing C plus minus multiply. So like, okay, we at Google don't like exceptions. Most people know that. But a lot of people write a subset of a C++ with a superset of like libraries or things they built around. And like, I can sometimes even guess who wrote the code. Like we have a tool that anonymizes code review. But I can guess who wrote the code by just looking at what they wrote. And like people come up with this, I want to use dialects, but not in a MLIR sense, but like language dialects they write. And we need to encourage and support that. And that's one of the things I would like to have as a proper connection is when you can add features into a language without actually modifying the language.
Right, well, so that's maybe an interesting research direction.
Yeah.
But maybe we should...
Recording in progress.
Thank you.
Maybe we should scope it to how to make the existing thing better without making C++ even more crazy.
Yeah, or we can make it less crazy. Like we can cut...
That sounds... I would love to see that.
Yeah, but we can pretend some things are too complicated to support, so we want to cut them out. But even that is not simple.
Well, so I mean, so I love Polygeist. I love your work on that. I think it's super awesome. It's been very helpful for people working with that community. So if that was a good thing, I'm going to say the bad thing. The concern I have with the Polygeist approach for Clang. So Polygeist is a different thing, and like I think it's awesome, but for Clang itself, I don't think we want to set the goal at a subset of the language, right? Like as Johannes was talking about, like such a long jump, that's a thing. It's a horrible thing, right? But it's a thing. And so if we enter a path where we say that there's a subset of the supported, the tasteful subset is supported and everything else isn't, then what we'd end up having is two paths forever. And two paths forever is not good, right? I think it's very important that we start by scoping and saying, yes, let's build the general solution, and then the general solution can be specialized for specific cases later, fine. But you have to set jump, long jump, fine. Like variable length arrays or whatever, I mean, yuck, but.
Well, maybe it gets deprecated while we are building it. Like Z specifically?
Well, I mean, what is C++ deprecated? It's deprecated the goofy trigraph stuff, but Clang still has to support it, right? And so like your notion of deprecation and Clang supporting is maybe separate. And what the committee does is more of like a suggestion for what a production compiler that has to build the world's code does, more than a feature specification, right? So.
And I think what's difficult there is that we may want to support all of C++, but we need a progressive way of building this. It's not like we can go and like spend 5 years building like or rebuilding Clang on top of anything, MLIR or otherwise.
Well, so I mean, let me make this a Bruno question, which is, in my experience, MLIR is a good thing, but it helps with the substrate part of the problem, and you still have to actually design your IR. And IR design is still hard. I haven't seen a solution for that.
It is very hard, yeah.
And so how do you approach that, and how do we know what a good CIR looks like? How do you think about that?
We've been trying to approach this in a very humble way, which is, well, as we try to address the use cases we care about, like for example, in our case, we care a lot of coroutines, which is a very idiomatic C++, abstraction that, we believe that if we solve some of the challenges we have there, we are also going to be able to do a lot of the other library things we would like to do on top of it. So it has been a mixed feelings. They show up very often while doing that design because, it's like, why I'm doing this if I don't have yet a pass that needs this information? So there's an iterative process on creating operations and trying to map things from the language and actually being able to use those. Otherwise, you're just put there because they look nice. But that's not all you need.
Well, another challenge that, so I haven't worked on your thing, I don't know enough about it, but a problem I imagine exists is there are these things that are tantalizingly close to what you want. So the SCF if statement or something, right? Or the affine parallel, whatever, that are actually completely wrong for the general case. Like you can't break out of SCF. For example, and you can't take breaks. There's no tasteful subset of C++ without break statements, right? And so I feel like again, my experience with this is building those very high level abstractions really do need to map the domain. And then you find yourself not just building that, you're building now a lowering pipeline.
Yes, exactly. So for example, one thing we've been doing, because at this point we're more working, we're first like targeting some analysis on top of it, which is incremental way to get all the way through the pipeline. And we already know that like we're kind of relying a bunch on structured control flow for having some nice properties of lifetime. But we know that real code has a bunch of go-tos and weird stuff, go-tos that go like inter scopes and all that craziness. But we believe that we can do things for sane code, and we can do as much as possible up to a certain level that will require, let's say, flattening all the scope things we do, so that thing will look like just a big CFG like we have in LLVM. And then some of the problems that are usually already solved in that area, we can get a path that just do what the status quo does, and then later on we can see what improvements we can do on top of that.
I mean, that totally makes sense. And Alex, just to come back and plus one what you were saying with subsets, right? There are domains in which a subset can be really useful, right? And so if you look at GPU programming, for example, I think it's reasonable to say, okay, you have to use structured control flow and you can't use goto and long jump when targeting a GPU, right? And so, maintaining structured control flow when you have it, I think is very valuable, right? And make divergence and like all these things so much easier to deal with if it's part of the whole pipeline. But that doesn't have to come, you can do that without loss of generality, WLOG, for all the weird stuff. And so I think that's really the art.
Yeah. So just hooking a bit on the polyguide stuff, we believe that polyguide is a very it has been able to compile and build lots of things already, and also we see it as a very important step into actually getting code gen working for real as part of developing something like Clang IR. So I'm really happy that we're having these discussions with both Alex and William on how we can try to bridge Clang IR and polyguide so that we can have an easy path for at least showing that we have a code gen solution. It might not be the one we want for the long run, let's say, because there are other use cases, but it's one that allows us to prove that it works, prove that it's useful. Because we're it's me and Nathan Lanza over there working on Clang IR at this point. We want to have more people helping us, but we got to be humble and do it incremental. It's a big problem. We need
I'm glad you're doing
from
that,
the community.
even because just the design space would be so large to tackle it all at once.
Exactly.
Yeah. Going back to what the goals are, and Johannes, you're a guy who likes OpenMP, for example, right? I don't think in loop transformations and things like this, LLVM has gotten so much complexity added to it because it's the wrong level of abstraction for things. And so, again, I don't know enough, but I've heard that in the OpenMP world, there's a lot of LLVM IR level things to hoist things out of OpenMP parallel for loops and things like this. And at the LLVM level, that becomes this interprocedural API changing transformation, which is a huge challenge. And so if and when this whole thing got done, which again is a epic journey maybe, I would love to see the LLVM pipeline get way simpler, because suddenly it's you move it out of a region into an enclosing space. And
the difference is, it is an interprocedural rewriting, hoisting thing, yes, but it's not specific to OpenMP. It actually works. It also does regular code, hoists interprocedurally stuff out if it feels that it's worth it, and so on and so forth. So we can build tools, high-level optimizations on the right abstractions that are not tied to something, while if we go in the OpenMP dialect world, we actually, either we use the same abstractions as we do in IR now, which will be one way, or you have to explicitly teach your transformation, this is an OpenMP parallel. Data sharing attributes mean the following things. If it's a first private, you can't just hoist it because you need private copies of it, yada, yada, yada. So, and we don't have that anymore because we're low level. So there is benefits to it and there's drawbacks to it. And then we try, currently we go the opposite approach. We add generic annotations to things in domain knowledge to help us do high-level transformations on this.
Well, so MLR doesn't prevent you from writing
absolutely
the general
not.
paths that does interprocedural,
No, you could
blah, blah,
do absolutely
blah
the same
stuff,
thing. I understand that.
But it just makes it way easier to do the simple thing. Can I ask a very specific nerd question, maybe to Mehdi?
Nerd, and you think about me?
Yeah. So, I'm reading about MLIR. It looks like a cool thing. How do you do indirect go-tos?
Indirect go-tos.
So Clang and I think Fortran or C, GCC, I don't know. The C family have the ability to take the address of a label, and then some number of places can do an indirect branch through a thing, and it can go to some number of things that had their addresses taken.
Right.
How does an MLR guru like you think about this?
In general, I would say, do we have to? Don't? Right? I'm
Alex,
camp.
come on.
Yeah, exactly. I'm in Alex camp on this.
Clang apparently has some users, I hear, and maybe they don't want their code broken.
About inline assembly or something like that?
No, inline assembly is easy. MLR already does that.
So maybe Mehdi can comment on cross-module optimization support, how easy is to re-implement TNLTO or something even better, having high-level IR.
Yeah, cross-module optimization is interesting because it's a domain that's always going to stress the compiler infrastructure. Most of the compiler infrastructure, and in general, whether it's LLVM or MLIR, is designed in general for single module optimization. This is the standard pipeline. This is the way we operate. And historically, LLVM has been doing cross-module optimization with this full LTO mode, where, again, the solution is to get back to the single module situation, right? Because that's where we have tooling, that's where we're comfortable, that's what we know how to handle.
You have use def chains for global variables that are all
exactly.
like disarmingly convenient looking, but also very problematic if you care about parallelism.
Absolutely. And so when we get to cross-module optimization, if we look at what we did with LTO, for example, it's been a lot of infrastructure building for breaking this single module assumption. Part of the problem is that then we build a parallel infrastructure. Like ThinLTO has summaries, it has its own full graph for the program and a bunch of analysis that performs on that, but none of the tooling or the APIs or what you do are, LLVM. It's a parallel world, right? And because you build the infrastructure only for the purpose of this cross-module optimization, it doesn't get as much mileage or as much, love as the rest of the infrastructure, and it's underserved. So it doesn't serialize or deserialize the same way. Something that's great about LLVM IR is this, try representation, the textual representation, the bytecode, and in-memory representation that you can always convert to, those kind of things. Another problem will be scaling, right? It's as soon as you get cross-module optimization, you get larger problem, and there's a question, how do you scale that? So regardless of whether you want to use MLIR or not, even if we were to use, adopt some dialect substrate in LLVM like Nicolai proposed, or anyway, we want to solve cross-module optimization, there are like 3 things that MLIR does today that can be helpful. One is that because it's much more flexible, it has this region nesting. You would be able to represent in a single entry point multiple modules nested at various levels and build your structure of your program differently. Another thing is the context.
Just to interject a little bit, I think the GPU people are doing this, where you have like the host and the device compute. And
exactly. There have been proposals, I think Johannes worked on this for LLVM, but MLIR supports this very easily to have your host program and multiple kernel or device in the same representation because of this hierarchy that you can express.
We did that part. Yeah, so we did that part in MLIR for a research paper because everything is research. But there's a lot of things you can do by just being able to move code around. And in MLIR it was trivial. Like, you literally move code around.
And just to touch on this, yes, we tried, and we have a prototype for LLVM IR to do this. The problems that come up are, they're not all unique to LLVM IR. Some are, and we would need to solve them. They're just unique to the infrastructure. A lot of those we could solve. And then there's the ones that are not unique to the infrastructure and might be interesting to just look across the pond. At that point, it wasn't really as far, and see what you did about it. And the thread has a lot of information about it and a lot of potential problems that have to be considered. So if anyone is interested, go look up the thread. Sorry.
Yeah, no problem. On the scaling aspects, we get the limit of the context. So in LLVM context is the units that you have to use for threading. And you cannot operate on IR if you want to load 2 modules and do cross-module optimization. If they are in the same context, you can compare data structure across, but you cannot use threading to operate on those 2 modules. And if you use separate context, you lose the ability to compare pointers and any structure that the context contains. Something that MLIR took great care of is to build the context in a very thread-safe way, meaning the context, you can load 2 modules or different part of the IR, the same actually IR, and process it in a threaded way, even modify it in a threaded way, because all those context data structure are thread safe. So that's another big element of scaling cross-module analysis.
Quick poll across the people sitting here. Who thinks we get threading on LLVM IR level at some point in the future, such that we have a context that is thread safe and we actually execute passes in parallel? I'm just curious, and maybe some people are as well.
We can poll the audience,
we can also poll the audience. Who thinks we'll actually get there at some point? At some point means at some point. It's like other things.
Well, do you find that the LLVM dialect in MLIR when
no, LLVM IR level, LLVM substrate. So LLVM IR rather than MLIR. So it was 3 people in the room. Interesting. Cool.
Yeah. Well, so I think that again, it's very difficult to explain unless you're there. But MLIR, the substrate, not the dialects, but the substrate, was built with full knowledge of LLVM, and it was built roughly 15, 20 years later than LLVM was. And so there's a lot of knowledge that had been accumulated in many other projects. And so the engineering is also just better in some ways, right? And so threading is obviously one of them. Multicore is not just the future. Apparently, it can be 100x speed up on modern machines, right? And so there's like many aspects that go into that. Also, the API is cleaner, right? Just the design, LLVM, the C++ API is wildly inconsistent with like, are things capitalized or not, and like just stuff like this, right? And so none of these things are the reason that it would make sense, but if there's a good technology out there that does solve lots of problems, and many problems that matter to different sub-communities, right? I think that there's a very real question about like, why not switch LLVM over, right? And on the one hand, you have the value, like inertia will always keep you the same, and you have a high impulse pressure required to change something with a lot of momentum, and that's a logistical problem to have, right? But on the other hand, if LLVM ossifies and doesn't evolve and becomes this old thing, then what you're really looking at is something else coming and replacing it. And I personally don't want that to happen. I think LLVM is pretty cool. But that's how technology works, right? And I think that if LLVM did not evolve and it did become the old thing and there was better tech, I would hope that the world would move to the better tech, right? And so I think there's LLVM engineers and people who care about LLVM, like the ball's in our court to make sure that it doesn't just become this obsolete thing because we don't like change.
Thank you. So I think we have 3-4 minutes. Let's hear panelists' opinion on some new promising developments in this area briefly. Maybe starting from you, Chris.
How about you not start with me? How about you start with Johannes? He asks good questions.
The most interesting thing in like big change that I see that I'm interested in is dialects. Nikolai's let's do LLVM dialects in a more direct way, and I'm really looking forward to both the talk and seeing if we can actually go there, because I believe learning stuff and getting these things closer together might also lower the inertia to change and actually adopt the other thing. So that's my biggest point.
Yeah, I would say something more or less along the same lines, which is, let's say with Clang IR, being able to build the bridge from the Clang AST. There are multiple pipelines of things we can explore on the GPU side of things, on the static analysis of things, or just plain C and C++ code generation, and get those very specific, tailored for different uses is something I've been looking forward to see.
No, I'm going to skip and let Chris.
Do you want to go? Okay.
You're not excited about stuff anymore?
Okay, well, okay, so fine. I'll go then. Shame me. See how you are. I still love you, man. The thing I'm excited about is this conversation, right? And the reason for that is that I wear many hats, okay? And so the technologist hat, I read about this cool thing called the MLIR some time ago, and I thought it was pretty exciting. And so the technologist says, hey, we should use the new shiny tool, right? But then the LLVM project, caring about community and evolution over the course of like the next 20 years, says, whoa, 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 new things might be dangerous, right? And so it's really interesting to me, just from this US dev meeting to the last one, which was 3 years ago. Last time we talked about similar things, the conversation was, oh yeah, MLR seems dumb. I don't know why people would use that. LLVM is fine, et cetera, right? And what has happened in the intervening 3 years is that enough people have started looking at MLR or have used it or built a project or built research with it or whatever, that there's a much broader understanding of MLR isn't magic, right? It has pros and cons. And the nuanced trade-offs of how you design and build things really matter. And so I think that, fast forward a few years, maybe the pandemic actually helped in some weird way of like mediating progress a little bit. I think we'll get a better result. Right? I think that factoring in the cost to the project in terms of, if we do the wrong thing, like running quickly into creating a mess, it comes at a huge cost to the community, right? And so I think doing this in a balanced way and doing it with a pretty good community knowledge of what MLR is useful for, I think is valuable. And so that makes me happy.
Thank you. So, no comments?
No, come on.
No, I mean, I was trying to get back to the C++ thing, but indeed what I'm really excited about MLIR is still to make compiler more accessible, more flexible, explore new ideas in a much more easy way, like lower the cost, because anytime I have an idea about something and I want to do something exciting, there's going to be people like Chris was going to say, like, no, go away and prove your things and make it work before.
I hate new things.
Yeah, exactly. Some very
Always
conservative
skeptical.
people,
Yes,
skeptical. And MLIR lowers the cost to me of exploring those new areas, those new ideas. If MLIR was around to do cross-module optimization, you could build your analysis and serialize it much more easier with MLIR than having to write your own bit code level, bit manipulation for just proving your point, right? So, unleashing new innovations, basically, in the compiler domain is really what excites me. And I love to see all the research and the new papers that comes that are using MLIR or just compiler technology in general.
Nicely said. Yeah. So you are keeping your ideas for tomorrow meeting.
No, I can talk. But I am kind of liking the weird situation we have now with MLIR and LLVM IRs that are sometimes like parallel, maybe seen as competing, but what they actually allow us to do is they allow us to think about the core concepts that we need to build a compiler. So now we discussed how do we design all IRs, all compiler IRs, and I don't think we would be able to discuss that with only LLVM IR or with only MLIR. And this gives us a different, higher level perspective, and we are focusing on things that are, well, I'm in research. I'm interested in hard questions that don't have answers. and now we are creating a lot of those. And what does it mean to represent something in a compiler? What does it even mean to have a program? And how do we build these things? And I think by having these two projects together and slightly in parallel, but slightly divergent, it's kind of valuable to actually be able to think about that and to think, how do we transform things? What are the parts that matter? I don't even have words for those because I don't want to coin a term it's going to be a dialect or it's going to be an attribute or something. There are concepts that we actually are still figuring out what they are, but those are really important. It's important to take time and get those right.
So you're talking about compiler 3.0.
Yeah, more like 42.0 before we figure it out.
Okay, so we have almost 30 minutes for questions from audience. Please. Do you have questions?
Hello? Hello? Testing? Okay, yeah, so there are two mics, and I'm going to be running around like a weirdo, handing mics to people in the middle. So you guys can, if you have questions, you're near one of these, you can line up. And if there are no questions, then I don't know. Okay, cool.
Thank you. So MLIR is better, kind of simplifying things, because it's easier to express constructs that are hard to express in LLVM IR. So my question is, but the substrates are not compatible, so it's painful to move from one to another. So if we found better ways to represent some constructs that are not representable or hard to represent in MLIR, we will have the third kind of substrate which will be incompatible. And from today's morning talk, we know that it's multi-year effort to move from LLVM IR to MLIR substrate. Maybe we need to think about the strategy how to evolve substrate part to make it easier for everybody. Yeah, what do you think about it?
I personally agree with you completely, right? I mean, I don't think that improving the architecture of Clang means that we stop improving LLVM. I mean, one thing we could do, which I think probably half the people in this room would be very grumpy about, is go rename all the LLVM APIs, right? I mean, make them all more consistent, make them all whatever. It would cause all the people with downstream changes to be very, very, very grumpy about that, but you could then start moving both sides of this equation. And I don't think that we're in a big risk of having 3 substrates. I guess that's one point I didn't understand. MLIR is not itself a static thing, and so we can move all of these things, for sure.
I mean, so one thing about, you said you can define something easily, but then you don't, the lowering might be a problem. Is that what you tried to say?
Yeah, for example, regions.
Right.
They're hard to represent them in LLVM IR. You basically what I see the approaches people are taking, defining intrinsics, starting to like dominate the block in something like this.
Right.
MLIR have this good constructs of the region,
Right.
but you have to do the support in every pass to make it work in real life. If something we will have in the MLIR or the next IR that are like will represent something even better, we probably will make the existing at that time passes, MLIR passes, incompatible with this representation.
Okay. That was the third substrate.
Yeah, this
thing.
is the first substrate kind of
So
thing.
one of the things that I think many folks don't, so there's differences of opinion, I'll only give you my opinion. One thing I find surprising is that people assume that every MLIR pass is supposed to work on every IR. And that's actually not the case. It turns out, if you look at a compiler like Swift, for example, there are diagnostic passes that happen on SIL, and they have very hard invariance on what order they run in. They're required for correctness. Like there's things that are very, very, very specific to a context and a set of assumptions. And then you can have your constant folding pass or something, which is completely generic, right? Mm-hmm. And I don't think it's a goal to make everything completely generic. I mean, that could be interesting for research, but I don't think that's a goal, right? The goal is to architect and engineer the best thing. And so, I don't think that's a challenge.
Yeah, this is a trade-off. If you do everything generic, you will not be able to implement and work it.
Yeah, but again, personally, I don't think any practical implementation would do that, so I don't spend any time worrying about that.
Thank you.
Yeah. I mean, you can make things.
So real quick, this panel goes to 2:25. If my watch is right, that's a minute left. I don't know if that was my mistake or what, but so I don't know how these things work. So the next panel starts in 5 minutes, according to
we get our timer says we have 9.
Okay, sure. I trust you guys. So go ahead. Right here. Go ahead.
Okay, then I'll make it quick. So one of the points that came up is that today MLIR is quite a bit cleaner than LLVM, in part because things were learned. I wonder, in your opinion, how much of that is just a sheer question of age, since code tends to accumulate cruft, and what will MLIR look like 15 or 20 years from now in that?
Before the MLIR experts answer, maybe in addition to that, what is, because there's just features we know we will need are not there yet, like undef and poison semantics and all of the other cruft that we have to add as we go along. So is that?
What do you think, Mehdi?
Yeah,
I've been talking a lot.
No, I think that's a very good point. Like the weight of the age of LLVM, is there definitely, but I think naturally in the way MLIR is structured, in this much more layered, the layer in MLIR are much more strict in extracting the substrate, makes it more robust to age, I think, from this point of view. That said, dialects themselves and passes that will operate on dialects, if you created your own LLVM compiler within MLIR, this component itself could also end up in the same way, right? So I think we managed to create better layers for all the substrate of the infrastructure. That's not bulletproof against passes and other things.
Thank you very much for all the discussion, really useful. I want to extend a little bit of the question that Johannes asked earlier, but in a different direction. The reason why I believe that Johannes wants to be able to understand the threading model within the IR level is because we need to somehow understand the semantics of the parallelism and the semantics of the execution such that we can make better decisions on that front. So I agree that probably threading is not the best abstraction, but I want to hear the take on, okay, how do we actually enable that information? And if we are using MLIR, how do we enable that information in a way that is traversal across the different levels of multiple IRs?
Well, wait, what is the alternative? Is the alternative LLVM IR or is the alternative an AST?
So
because LLVM
I don't really
doesn't capture any of this.
It's not a magic bullet that has a solution for this.
Okay, you're asking how best do we solve problems like this?
Right, like how do you imagine, are we going to be building ad hoc solutions for each IR where we say, okay, here is how the parallelism works on this IR, and here is the parallelism works on that IR. And then we're going to put all of them together, and how are they going to correlate?
So again, having built several compilers with MLIR now, right, one of the things that becomes surprising and interesting is the decomposition of the problem that you get. And so Johannes mentioned the benefit of having dialects that compose, right? And so you have dialects, and you can have multiple different domains that then mix. You can have an OpenMP dialect, you can have a C dialect, and now you have OpenMP and C. You do that. And therefore, you can have lowering, and you can say, I'm lowering away all the OpenMP stuff, and you can like architect a compiler. One of the really interesting things about this is it gives you a way to reason about phase ordering. And phase ordering, no matter what substrate you want to use, is always a thing. You have to architect a compiler and a pipeline and decide when and where things get lowered out. And so if you're talking about threading parallelism stuff, right, you're going to have some part of the compiler that deals with that. And heck, build your abstractions that are very specific to the model that you're using and be very concrete about that, and have passes that are very specific to even the operations, right? I don't like to build things that are fully generic first and then try to apply them to a specific problem. I like to build things that are very specific first and then generalize when you understand, when you have more models for the same problem, right? And I think that MLIR gives you a lot of tools for doing that, and I think that's one of its strengths.
It lets you build more than one, and what we generally saw in MLIR is when we have built like 5 different specific representations for, well, we don't have them for parallelism entirely, we have them, for example, for side effects or for memory. So at some point, we see that there is a generic notion of what a side effect is or what a parallel effect is. And then we start modeling those that are generalized away from a concrete IR. So I think like what MLIR lets you build is this core concept of I need a parallel IR. There are things that are executing concurrently. There is a synchronization point, but that's it. And then you can build a lot of compiler logic around that without necessarily caring, oh, I'm an OpenMP, or I'm an MPI, or I'm whatever weird parallel thing you can come with.
Thanks.
But you still have to design it. That's the problem, right?
You need to design it several times before you get it right.
Yes.
So one of the big advantages of MLIR is that it comes with a lot of extra flexibility, like for instance, all these regions and multiple return values, but that flexibility also comes often with a much bigger burden in order to fully use it. As an example, if you wanted to make a fully general version of finding all the predecessors to a generic block that has completely unknown types of operations as the terminators, it's very, very non-trivial to write this, whereas in sort of a more LLVM style, this is a little bit easier to write, or as an example, if you knew the specific dialects. So my question is, how much of the, say, C and C++ specific optimizations will rely on, say, a C++ specific dialect, a general MLIR dialect like Arith or SCF or CF or something like that, as opposed to the completely generic MLIR operation?
Well, so yeah.
Well, we're still figuring it out. It's a hard problem.
I think it's a trade-off, but if we take what Chris and Alex were saying earlier, you start specific, right? So you build your path for the CIR as much as possible because that's what you do, right? And then you generalize as needed, if needed. It may not ever be needed to support the full generality of as many nesting you want in MLIR if you just focused on a path that is meant to support the Clang IR.
And just for the audience, full disclosure, William here wrote polygeist code that was just writing stuff around it.
We have to stop here, guys. Thank you. Let's thank our panelists. Thank you.